Welcome to our journey through the fascinating world of mathematics. Today, we'll explore 15 incredible mathematical concepts that have shaped our understanding of the universe. From the building blocks of numbers to the geometry of space-time, we'll uncover the hidden patterns and elegant equations that govern our world. Get ready to expand your mind and discover the beauty and power of mathematics. Buckle up, it's going to be a mind-blowing ride. As mas anxieties.
Prime numbers, those divisible only by one and themselves, are like the hydrogen and helium of the periodic table, the fundamental building blocks of larger numbers. Every number can be broken down into a unique product of primes. Prime numbers secure our online transactions and communications.
Pi, the ratio of a circle's circumference to its diameter, is more than just a number you memorized in school. It's a universal constant baked into the very fabric of reality. Wherever you find circles, from the ripples in a pond to the orbits of planets, you'll find pi. But here's the kicker. Pi is irrational. Its decimal representation goes on forever, never repeating, containing every possible number combination. From the equations governing the behavior of light and sound waves to the distribution of galaxies in the universe, pi makes its presence known. So pi isn't just about circles, it's a fundamental constant woven into the tapestry of the cosmos.
Zero might seem like nothing, but in the world of mathematics, it's everything. Before its invention, civilizations struggled to represent the concept of nothingness. It was the ancient Indians who first recognized zero not just as a placeholder, but as a number in its own right, a revolutionary idea that changed the course of mathematics. Zero gave birth to algebra, allowing us to write equations and solve for unknowns. Imagine trying to do that with Roman numerals. It unlocked the power of negative numbers, paving the way for complex mathematics used in everything from engineering to physics. So, the next time you see a zero, remember, it's a symbol of profound mathematical power.
The golden ratio, represented by phi, is approximately 1.618. This ratio is found in nature, from sunflowers and seashells to the human body. The ancient Greeks used it in their art and architecture, like the Parthenon. Today, artists and designers use the golden ratio for visual appeal. So, when you see a sunflower or nautilus shell, think of the golden ratio.
The Fibonacci sequence, where each number is the sum of the two preceding ones, reveals a hidden harmony in nature. Look closely, and you'll find this sequence woven into life. Count the petals on a flower. It's often a Fibonacci number. The spirals in a pine cone, the branching of trees, the arrangement of seeds in a sunflower, all follow this sequence. The Fibonacci sequence is connected to the golden ratio. It's a testament to the interconnectedness of mathematics and nature.
Infinity, a concept that stretches beyond the grasp of our finite minds, has fascinated mathematicians and philosophers for centuries. It's not a number, but an idea, a concept representing something boundless, endless, larger than any quantity we can imagine. Think of the largest number you can. Infinity is bigger. Infinity pops up in unexpected places, like the infinite decimal expansion of pi or the concept of a line extending forever. While we may never fully grasp the vastness of infinity, grappling with this concept pushes the boundaries of our understanding.
The Pythagorean Theorem, a fundamental principle in geometry, states that in a right-angled triangle, the square of the hypotenuse, the longest side, is equal to the sum of the squares of the other two sides. This theorem has been known for thousands of years, with evidence suggesting its use in ancient Babylon and Egypt. It forms the foundation of trigonometry, allowing us to calculate distances and angles. The Pythagorean theorem is used in navigation, surveying, architecture, and even in understanding the relationships between space and time in Einstein's theory of relativity. So, the next time you see a right-angled triangle, remember the Pythagorean theorem. Imaginary numbers, often met with skepticism, are essential tools in mathematics and physics. The concept arises from the simple question, what is the square root of -1? Since no real number, when multiplied by itself, produces a negative number, mathematicians invented a solution, the imaginary unit, denoted by the letter I, where I squared equals -1. Imaginary numbers have revolutionized our understanding of the universe. They are crucial to complex numbers, which combine real and imaginary parts. Imaginary numbers have very real applications in fields like electrical engineering, quantum mechanics, and signal processing. Eulers Identity, often hailed as the most beautiful equation in mathematics, combines 5 fundamental constants in a simple and elegant relationship. E raised to the power of I times pi plus 1 equals 0. The beauty of Eulers' identity lies in its simplicity and profound implications. It connects algebra, trigonometry, and calculus. The fundamental theorem of arithmetic states that every integer greater than 1 can be expressed as a unique product of prime numbers. This simple yet powerful concept is the cornerstone of number theory, revealing the fundamental building blocks of all whole numbers. Just as atoms combine to form molecules, prime numbers combine through multiplication to create all other integers. This theorem has profound implications for cryptography, coding theory, and our understanding of the distribution of prime numbers. So, the next time you encounter a number, remember the fundamental theorem of arithmetic. Fractals, those mesmerizingly complex patterns, exhibit self-similarity at different scales. Zoom in, and you'll see the same patterns repeating endlessly. Nature is full of fractals, from the branching of trees to snowflakes, coastlines, and mountains. Mathematicians model phenomena like financial markets and bacterial growth using fractals. So, next time you see a snowflake or a fern, appreciate the beauty of fractals. Set theory, developed by Georg Cantor in the late 19th century, revolutionized mathematics by providing a rigorous framework for understanding collections of objects. A set, simply put, is a well-defined collection of distinct objects, whether they are numbers, letters, or even other sets. Set theory forms the foundation for much of modern mathematics, including logic, algebra, analysis, and topology. It allows mathematicians to define concepts with precision and provides a powerful language for expressing mathematical ideas. So, while set theory might seem abstract, it underpins much of the mathematics we use every day. Probability, the branch of mathematics concerned with the likelihood of events, helps us make sense of the uncertain world we live in. From predicting the weather to analyzing financial markets, probability theory provides tools for quantifying and managing risk. By understanding probability distributions and using statistical methods, we can make informed decisions based on data and analysis. Probability theory underpins many fields, including statistics, finance, physics, and computer science. So the next time you flip a coin or roll a die, remember that you're engaging with the principles of probability. Number systems are the foundation of mathematics, providing the symbols and rules for representing and manipulating quantities. From the familiar decimal system to the binary code used by computers, different number systems serve specific purposes and reflect different ways of understanding numbers. The decimal system, based on the number 10, is the most common system we use. Binary, with its simple 2-digit system of zeros and ones, is the language of computers, underpinning everything from digital communication to data storage. Understanding different number systems expands our mathematical horizons. Non-Euclidean geometry, a departure from the familiar geometry of Euclid, challenges our fundamental assumptions about space and shape. While Euclidean geometry, with its parallel lines and right angles, works well for describing objects on a flat surface, it fails to accurately represent the curved nature of space-time. Non-Euclidean geometries, like spherical geometry and hyperbolic geometry, provide alternative frameworks for understanding space. These alternative geometries have revolutionized our understanding of the universe, playing crucial roles in Einstein's theory of general relativity. So, while non-Euclidean geometry might seem counterintuitive at first, it has expanded our understanding of the cosmos. Thanks for joining us on this mathematical adventure. We hope you found these concepts as fascinating as we do. Don't forget to like, share, and subscribe for more intriguing insights into the world of science and mathematics. From the elegance of Eulers' identity to the infinite complexity of fractals, mathematics offers endless opportunities for exploration and discovery. Keep questioning, keep learning, and keep marveling at the beauty and power of this universal language. So, keep exploring, and who knows what incredible discoveries you might make.